I'm Mike Lockwood. I'm a professor of space environment physics at the University of Reading, and I research long-term change in the sun and how that affects us here on Earth. I started off, believe it or not, looking at aircraft-to-ground radio communications, and a lot of those are done through the ionized upper atmosphere, the ionosphere. And then I started working with a radar system in northern Scandinavia that looked at the ionosphere called IceCat. It's a joint European project, rather wonderful project actually. I really enjoyed it, we had a fabulous time. And northern Scandinavia is a fabulous place too. So, but that brings in the aurora. And then I began to realize, well, associated with aurora is a phenomenon called geomagnetic activity, which is how much variations in the sun shakes Earth's magnetic field. And I began to realize that we could use the historic data on shaking of the magnetic field, because it goes back a long way, right back to Gauss in 1832 when he built the first proper magnetometer. So there was a rich record of these geomagnetic fluctuations to tap into, and I realized it could tell us something about the variability of the sun. So by applying all the research I'd done on the ionosphere, because a lot of that geomagnetic variation comes about from currents that flow in the ionosphere. So all that research I did was really useful, and I could unpick the elements in why the geomagnetic variation had changed into working out what solar change was. And that's been a really useful constraint actually in the irradiance studies. One of the reasons why 20 years ago people thought the solar radiance between the Maunder minimum and now might have changed quite a lot, although it would still actually be quite a small radiative forcing compared to greenhouse gases. But it was overestimated because people were drawing analogies between our sun and what they called sun-like stars. It turns out those analogies were nearly all invalid. So it also turned out that the surveys that we used were very, very limited. Very limited number of independent stars were used. When that was realized, it was thought, well, hang on a minute, we don't have any way now of telling what the Maunder minimum sun was like. You know, we used to draw analogies to some stars out there, but if we can't do that, what have we got? So my stuff on how the magnetic field of the sun had changed became very, very important, because it could be used as a constraint on a whole new generation of how the solar radiance has changed between the Maunder minimum and now grew up, based on fitting the solar magnetic field that I'd inferred from geomagnetic data. So it provided a new way in. And as I say, those estimates produced a much smaller drift in solar output between the Maunder minimum and now than we thought before. And the recent solar cycle is proving them just about right. It was all a classic example of how in science you look for one thing and you find something else. It really was. Everybody knows that our climate's driven by the sun. And so it's not a difficult step to imagine that changes in our climate must be driven by changes in the sun. The problem is that changes in the sun are actually very, very difficult, and rapid changes are almost impossible. And the reason is that our sun is very, very large. It's a huge ball of gas. And the important part is the outer part of the sun, about the outer third, where you have, it's what we call the convection zone, the large cycles of energy flow, with energy brought up and then the cold gas and plasma falls back down in these huge circulation cells. Now the thermal time constant of that outer layer of the sun, the outer third of the sun, the convection zone, is about 1/10 of a million years. It's just so much of it. You can't heat it up and cool it down. And what the sun emits is largely dependent on the surface temperature. So one little calculation you can do is say, well, what if I turn the sun off completely? I stopped all the energy coming out of the core from the fusion reactions, and it gets to this bottom edge of this convection zone. What if I stopped all the energy coming through into the convection zone? Then 100 years later, here on Earth, the amount of power we were receiving from the sun would have dropped by something considerably less than 1/2%. all right? And that's a complete switch off of the sun. So it's because the sun is so big. It's so massive you can't change its outside temperature, and it's its outside temperature that determines how much it emits. So it's pretty constant in that, and in fact so constant we used to call it the solar constant. We used to actually say that the power output from the sun was completely constant. Then we found actually it does vary a little bit. It varies by about the largest variation we've seen is about 0.1%. Okay, and the reason that it does that is that you can get little surface features caused by magnetic fields on the sun. So those surface features are, the most well-known ones are sunspots. Sunspots are quite big bundles of magnetic field coming up through the surface of the sun, and they inhibit the energy coming up from underneath. But for every big bundle, there are lots of little ones, and in fact a big bundle breaks up into little ones, and the little ones paradoxically appear bright. They're called faculae. It comes from the Latin for torches. So for every sunspot there are 1,000 faculae. And so the net effect is that when there's a lot of sunspots on the sun is a little bit brighter. As I say, only about 0.1%. We used to try to measure what we got from the sun, because we know the atmosphere changes that, by going to the top of mountains and measuring, but it's still not a very good measurement from up there. And so really one has to get completely clear of the atmosphere into space to do the absolute measurements of how much power we're receiving from the sun. Trouble is, absolute radiometry, particularly from space, is a really, really difficult thing to do. It's very, very hard. And we've had a number of instruments up over the years. The difficulty comes in both intercalibrating those instruments. So when one instrument dies and another one comes, you have to make sure that they're well intercalibrated. But actually also the instruments themselves degrade quite badly, particularly this type of instrument. And you can have, one way that they could deal with that is they have two instruments on board. One they use very frequently, on which the degradation is high, and one they use very infrequently, so it stays nearly pristine, and you can work out what the degradation is, assuming the degradation is proportional to its use. So it's a very difficult thing to do, and it causes a lot of debate about how you put these measurements together. And there's really two philosophies. The Swiss have the philosophy that because it's difficult, you keep correcting, you keep adjusting, you've got to keep on top of, keep calibrating it all the time. There is a danger with that, and that is, of course, if you keep allowing yourself to correct a data sequence, you can turn into whatever you want. And so the American philosophy is much more, we just trust the instrument, we put it up there and we see what it gives us. But I actually believe that you can't necessarily do that, because the instrument degradation in this particular case is quite high, is quite a big problem. So even with that though, those two different philosophies, it really comes down to the big difference between what we call composites, these where we've taken different measurements and tried to make a long data sequence. Those composites differ largely because of one event, believe it or not, and it's in a period between, we had a good instrument on SMM, Skylab, that we lost, because we lost Skylab, crashed somewhere in Australia. That was called ACRIM 1. And then ACRIM 2 was on a satellite called UARS, the Upper Atmosphere Research Satellite. And the idea was ACRIM 2 would be available to take over before ACRIM 1 died, so you had some overlap to intercalibrate. Turns out that because Skylab came down early and ACRIM 2 wasn't ready, there's a gap between the two. So what they did was they went back to the first instrument they used, which was something on an old satellite called Nimbus 7. And it's known that in the middle of that period, Nimbus 7 had a pointing funny. It stopped pointing in the right direction. And the Swiss have corrected for that, and the Americans haven't. And that's why the big difference between the two all comes down to that one event. So, and the evidence is, a lot of people try to prove that models support one or the other. All the evidence kind of supports the idea that the Swiss have got it right. So I personally think that the reconstruction from the World Radiation Centre It's PMOD, it's a laboratory in Davos in Switzerland, and I think that's by far the best one myself. There are other people that like the other one because it kind of gives them the result they want, but actually when you look at it in detail, the evidence really supports the Swiss one. If you look at total solar radiance, which is what we call solar constant, now we know it changes a little bit. If you look at that, the variation that you get out of the Swiss, the PMOD composite, agrees much better with things like sunspots and cosmic rays and lots of solar indicators are. But actually the best test is probably what we call solar magnetograph data. This is solar magnetographs measure the magnetic field everywhere on the surface of the sun. And from that, we've got a really nice model. They call it the satire model, which I'm not sure is a good name for a science model, but it's actually very, very good. And it reconstructs how bright the sun would be just from looking at all the magnetic field on the surface. And that very much supports the Swiss composite, not the American one. We've had modern space measurements of total solar radiance and the magnetic field and the sun and things like that. And the magnetic field that leaves the sun and comes all the way to the Earth in what we call the solar wind. We've had measurements of those that are reasonably continuous and reliable since about the mid-1960s. So I'll call that the space age. So we've got really good information about how the sun has changed in the space age. The problem is, until very recently, the space age was dominated by rather large solar cycles, quite high solar activity. We've sort of just really come to realise that we've been living in what we would call a grand solar maximum. And we know that if we go back a few centuries, the sun goes into what we call grand solar minima, and the most recent one is the well-known Maunder minimum, which we now know was real, and there really weren't any spots on the sun, and we know from isotopes that are modulated by the activity on the sun that we find in ice sheets or in tree trunks. We know that the sun goes up and down between these grand minima and grand maxima. The question is, what information do we have about how the sun has actually changed? And the best record we've got is sunspots, because they go through, they do exist from before the Maunder minimum. They're a bit sparse, but we do have measurements then through the Maunder minimum, and we now know that despite the fact virtually no spots were seen for 50 years, people kept watching. So amazing testament to how patient some people are. And then they started coming back again and they increased. And as I say, recently in the space age, we had 3 very big cycles. And so the challenge was try to interpret our recent irradiance measurements in terms of sunspot number, so that we could reconstruct how the irradiance had changed. And estimates kind of changed over time quite a lot for a number of reasons. But they weren't really very well constrained. What's very interesting is this last cycle, the cycle we're in now, we're just about at the maximum of cycle number 24, we call it. It's really weak. It's incredibly weak. We haven't seen a cycle as weak since about 1900. And the irradiance has dropped on average, but not that much. And so actually, for the first time, we've got a bit of what we call dynamic range on the measurements. So we can actually extrapolate back to the Maunder minimum with a bit more confidence. Interestingly, the numbers that have gone into, say, the IPCC report are about right. What I think has changed is that if you look in the IPCC report, it will say that the level of certainty on solar change is medium. I think that could now be changed to high in the light of the recent measurements of what's gone on in the last solar cycle. We don't have a proper predictive model of solar activity. It's that simple. And the best numerical models we have of the sun are what they call 2.5 dimensional, which is a nice way of saying they're not 3-dimensional. Okay, and the sun is eminently a 3-dimensional body. And that kind of tells you where we are with solar modeling. We don't have a predictive capability. So all you can do is fix on some patterns, and there are some tricks that you can use to predict maybe 5 years in advance. The size of a solar cycle seems to be related to the magnetic field at the previous solar minimum. And you can use that, and that seems to work quite well, in fact. But we still argue about why that is working. So we don't have an understanding that gives you a proper predictive capability of solar activity, which means that it's kind of open season for, you know, having a go, because any one prediction is as good as bad as any one other one, and so it's quite fun to line them all up and see who got it worst wrong and who got it right best and things like that. You're not really learning much about the physics of solar variations by doing that, quite frankly, and the way to go is the same way the climate science has gone. We've got to have proper predictive models of solar dynamics before we can start to do that, and we're just quite a long way from being able to do that. So I think that's why people like doing it, is that, you know, it's like gambling on the horses, you know, it could go any which way. There is a whole area of science called space weather, and that is to do with how modern technological systems are subject to solar activity, and the effect of a very large solar terrestrial event on modern life could be quite profound. I mean, satellites are at risk, communications are at risk, all sorts of things are at risk. So it is quite valid that we worry about that. It's not so valid to worry about it in terms of the solar influence on global climate, because quite frankly nothing fits. The altitude profile of the warming is all wrong for solar warming. The difference between day and night has not increased as you would expect if it was solar irradiance induced. The seasonality is all wrong. Okay. In fact, we see more warming in winter, whereas if it was the irradiance increasing, you'd get more warming in summer. So nothing fits. It really doesn't fit at all. And there have been one or two studies that have tried to make the wiggles fit the solar variation, but when you look at it properly with proper statistics, you find that there's no statistical significance there at all. If you have enough free variables, you can fit anything. So I think from the point of view of global climate, there really isn't any major issue at all. But there is one thing that I'd like to point out, and that's the difference between global climate and regional climate, because I do think there's a growing body of evidence that solar activity variations can influence particularly winter climates in certain parts of the world. And those certain parts of the world are the American continent and here in Europe. In particular, both those places get cold winters when solar activity is low. That seems to be a statistically significant result. It's not a global effect, because if it's cold here and in North USA, it's actually warmer in Greenland and Canada and in the Mediterranean. There's what we call a quadrupole pattern that keeps appearing, and it seems to have a good relationship to solar activity. Now, why that matters is an awful lot of the anecdotal evidence for long-term solar influence on climate comes from early meteorological measurements made in Europe, particularly in wintertime in Europe. And so if one says, haha, this is indicative of a global trend, you're actually got a big problem, because actually you're selecting a very specific area where there may be something funny happening. Okay, so as I say, if we get colder winters in Europe, then there'll almost certainly be warmer in Greenland. It's to do with meanders in the jet stream, and warm air goes up to Greenland, and we get the cold air coming down from the Arctic. We call them blocking events, because it's this big meander in the jet stream is called a jet stream blocking event. And it looks like, through the solar ultraviolet effect on the stratosphere, this might actually be real. I think it is. I think the evidence is pretty, but it's contentious. There's big scientific debate about it. But what there isn't a scientific debate about is whether it's a global phenomenon. It is not a global phenomenon. And as I say, if there'll be a compensating effect, it's a redistribution of temperature around the North Atlantic. But it does impinge upon the global warming debate if people insist on using measurements from a small region at a certain season. They might get something that looks contrary to the consensus view. It isn't really. It's what's wrong is their assumption that they're regional, seasonal measurement actually is telling you something about global change. We did some research. I actually worked with the main guy at PMOD in Davos in Switzerland, a guy called Klaus Froelich. And we were able to show not only had his version of the solar irradiance been decreasing since about 1985, but every other solar indicator had. So in fact, cosmic rays had gone up, which means the solar activity that keeps cosmic rays low had gone down. Sunspots had gone down. Everything had declined since about 1985. Now, I know we've had a few years of so-called hiatus in temperatures, but essentially they've risen and flattened off. But that flattening off was much, much later. So if even that flattening off had something to do with solar, it's a very long delay, okay, before anything happened. So unless you invoked an incredibly long response time constant, that then you couldn't explain how the temperatures kept rising in the global average temperature, and yet all the sunspot activity indicators were declining. The only way to do it was to invoke this incredibly long time constant that meant that the Earth was like... And that doesn't fit, because we know, for example, volcanoes, we know what the response time constant is. We see the effect on global temperatures of a certain volcano pretty quickly. And why would blocking out the light with a volcano have a different response time constant to actually reducing the strength of the source of the light? It just doesn't make sense. So to me, that was useful confirmation that actually that the recent trends in temperature were nothing to do with the sun. They just didn't fit. I have tried very hard in everything I write to make it quite clear that I'm not talking about global climate change. And in fact, I did a paper with the guys at the UK Met Office where I estimated we took various estimates of how the total solar radiance would change if we went into a Maunder minimum within 50 years of now, which is about a 10% possibility, quite frankly. And we could make very little difference to the overall temperature rise, even when we put everything we could, all the weightings, it still made very little difference. So I have tried to make it absolutely clear that I'm not talking about solar influences on global climate. There are good reasons to expect them not to be there, and there's certainly no evidence that they're there, no credible evidence anyway. But I do think that it's quite possible that you can have these seasonal. They're nearly all in winter. That's a clue. It's because the jet stream is driven by temperature differences between the equator and the pole, particularly in the stratosphere. So in summer, when you've tipped the pole towards the sun, that gradient is reduced and the jet stream so the potential for modulating the jet stream is much lower than in winter when you've got a large gradient between the equator and the pole, and that drives the strong jet stream. But it does seem to weaken when solar activity is low because that gradient is lower, and that makes it more prone to these meanders, these blocking events. So there's good reason to expect it. The difficulty is getting the effect down to the lower troposphere where our weather and climate is, but it's beginning to show up in climate models that have enough layers up into the stratosphere that if they go high enough, they start to reproduce this sort of phenomenon. So I'm pretty sure it's there, but I also know it's not global. I mean, we've seen that in the data, that if we get a cold winter in Europe, it might be cold in Washington, but it'd be warm in North Canada, Greenland, and actually warm over the Mediterranean as well. So this quadrupole pattern that I talk about keeps coming up. There is an alternative hypothesis to jet stream modulation to do with the loss of Arctic sea ice. That's certainly possible. I do know a lot of people are slightly worried about the evidence, but I know a lot of people who are slightly worried about the evidence for the solar influence on it as well. So I think you take the both of them and you put them into a folder marked really interesting, needs further study. That would be my assessment of both of them, quite frankly. But I think that it's interesting. It's both interesting and it's quite possible and plausible. So. I do get quite often quoted as saying an ice age is coming. What I actually have put a number on is the possibility that the recent decline in solar activity that we have observed could continue all the way down to the next Maunder minimum. And I'd say that it's somewhere between a 10 and 15% possibility that that could happen in 50 years. I am certain it will happen within 400 years of now. I'm pretty certain it'll happen within 150 years of now, but 40 or 50 years, maybe a 10 to 15% possibility. And that's a statistically worked out number by looking at ice sheet records and things. The problem is that in some people's mind, something called the Little Ice Age and the Maunder minimum become synonymous. I had no idea how that happened because they don't even agree in dates. The Little Ice Age, as a global drop in temperature from things like tree rings and things like that, starts somewhere between 100 and, well, all sorts of estimates, but certainly at least 50 years before the Maunder minimum starts, okay? I don't like the term Little Ice Age at all. To me, it wasn't an ice age of any shape or form, okay? One of the things I've had fun doing is looking at a temperature record. It's called the Central England temperature. It's measured in a rural area between London, Bristol and Manchester. So it's well out of any, the measurements are always taken away from urban heat islands and as they grow and things like that. And it goes right back to the 1650s. Okay, now, if you look at those temperatures from the Maunder minimum, I think it's statistically true that there are more cold winters then, which is the solar influence on cold European winters that I think is potentially there. But they weren't unremittingly cold, and in fact the coldest winter in the whole 350-year Central England temperature record is 1683 to 1684, that winter. If you just shift on 2 years from there, so still right bang in the middle of the Maunder minimum, you have the 5th warmest winter in the whole Central England temperature record. So the idea that the term the Little Ice Age gives this impression that it was unremittingly cold, you know, all the winters were freezing. Well, no, actually there were plenty of warm winters in the Maunder minimum, certainly in Central England. The summers don't really show much difference between the Maunder minimum, you know, so I hate the term Little Ice Age, and I think it's abused. I think people use it to say it wasn't an ice age of any shape or form. It may have been a period of slightly lower global average temperatures, but it wasn't an ice age, and there's plenty of fluctuation level around it. So I think, to me, using the term is just playing with words. It's building your argument on a misconception. I think it's also quite useful to point out that if your logical argument is resting on the interpretation of a name given to something, it's not a good argument, okay? I think I could call, you know, anything to try and make a theory stand up, all right? But it's just bad logic. It's just bad, sloppy thinking to say, oh, that was a little ice age. No, well, think about it. It wasn't a little ice age. It was a period of slightly lower temperatures on a global scale, maybe. And as I say, most of the evidence for that comes from trees. It's actually what we really know is a period where globally summers seem to have been a little less good. Well, that's not an ice age by any means. The winters were more variable, if anything. So. I think there are some really interesting questions. Certainly anything to do with solar variability, where does it come from? If we're ever going to get on top of predicting it properly, we're going to have to understand that. So I think there's a whole lot of almost catching up to do. Until we've got solar models equivalent to climate models, we're never going to be able to get anywhere. So So I think that's really interesting. It's a very challenging area as well, actually. It's not easy. But there are some good missions coming up, like there's a European Space Agency mission called Solar Orbiter, and that's going to be really, really fun to look at that. It'll fly over the poles and look at the sun every which way, and we'll actually learn an awful lot about solar variability from that. And as I say, modelling's got a big part to play. So that's one area. This whole area of how stratospheric changes, because the stratosphere is undoubtedly under quite considerable solar control, but how does this thin gas at the top of the atmosphere percolate down and cause anything in the troposphere? As I said, I think the effects are not global. I think they're regional and seasonal and patchy and so one region changes one way and the other the other. But I think my belief is that they're there, and that becomes a whole interesting area. There's a really interesting area in atmospheric chemistry, in that sort of area as well. The chemistry and dynamics of the stratosphere have not been mixed up together very well in models, so that's interesting. I recently became a granddad twice over, and they're wonderful kids. I want the best for them, I want the best world for them, and I am seriously worried that actually if we don't start taking the threat seriously, understanding it and understanding how we can mitigate and control it, then I'm really worried about their future.